Our first lecture is going to cover a variety of topics that should mostly be a review from general chemistry, and these are going to be getting to ways that organic chemists think about bonding in molecules and really more practically drawing molecules. So this is going to correspond to sections 1.1 to 1.5 and 1.8 to 1.10 in your Smith textbook. So what we're going to try to talk about today is a review of Lewis structures or Lewis electron dot structures, especially thinking about how those are used by organic chemists. And we're going to learn some shortcuts for thinking about bonding in Lewis structures and something called formal charge to think about charge distribution in molecules. So before we do that, let's just take a brief review of some of the useful information that is in the periodic table. So you can see kind of abbreviated version of it right here. Okay, so there are a variety of ways of thinking about how the periodic table is organized, but maybe one of the more useful ones is that elements that are in the same row of the periodic table tend to be relatively similar in size. Not exactly the same. They get a little bit smaller as they move from left to right, whereas elements that are in the same column of the periodic table tend to have similar chemical reactivity. And the origin of that chemical reactivity has to do with their electron configurations. More specifically, the electron configuration in the outer or valence shell. Okay, so a couple of other things to note on this periodic table. On this one, each of these rows is indicated by a variety of electron orbitals. So in the first row of the periodic table, the outermost electrons, the valence electrons, are in the 1s orbital. In the second row, the 1s orbital is full, but then the 2s orbitals are filled up here, and there's room for 6 electrons in the 2p orbitals. So that's these 6 elements. And that goes on farther down the periodic table. Okay, so what we really want to be able to get pretty quickly from the periodic table is the number of valence electrons that any atom is going to have. Okay, and that is generally going to coincide with the column of the periodic table that it's in. So let's take a look at some of the atoms and elements that we're going to see the most. So organic chemistry is really the study of carbon. So carbon is the one we're going to see most often. Carbon is in the 4th group, and you can see here that we have 4 dots around the carbon, stating that it has 4 valence electrons. Nitrogen is in the 5th row, 5 electrons. Oxygen is in the 6th row, 1, 2, 3, 4, 5, 6. And hydrogen in the 1st row has 1, and the halogens, like fluorine, chlorine, and bromine, have 7. All right, so now let's take a look at talking about Lewis dot structures. So Lewis dot structures are very useful in organic chemistry for describing covalent bonding. That's a situation where 2 or more atoms are going to share electrons, typically in pairs, so that each of them can have a full valence shell. So that's going to be 8 electrons for most elements, and only 2 electrons for hydrogen. And when we have pairs of electrons that are shared between 2 atoms, we call that a covalent bond. Okay? So let's think about how many valence electrons we would have in this molecule here, methane, CH4. So carbon has 4 valence electrons. I'll abbreviate that V, E minus. Each hydrogen has 1 valence electron, so that's a total of 4 valence electrons. So our goal now in drawing a Lewis dot structure is to use all of those valence electrons and to place them either in bonds or in lone pairs, non-bonding pairs, such that every atom has a full valence shell. So it's going to be 8 for most atoms, 2 for hydrogen. So for methane, this is ridiculously easy. We just put a bond from the carbon to each of the 4 hydrogens. That uses up, so we have 4 bonds, each of which have 2 electrons. That's our 8 electrons total. Okay? Now, if we do the same thing for ammonia, for NH3, nitrogen now is going to have 5 valence electrons, and we have 3 hydrogens for a total of 3 valence electrons, and so that's going to be 8 again. Okay? Well, now when we put bonds from the central nitrogen to the 3 hydrogens, that uses up 6 of our electrons. We still have 2 left, so that means we are going to have to put a lone pair on the nitrogen. So both of these molecules have 8 valence electrons. In methane, CH4, there are 4 covalent bonds. In ammonia, NH3, there are 3 and a lone pair. Now, one last calculation that we can do after we have drawn a valid Lewis electron dot structure such as this is a quick calculation known as formal charges. And formal charges give us a very kind of quick and dirty way to identify charge in a molecule. Okay? It's not the only way, but it can be a very useful way. And there's a relatively simple formula for doing that. So the formal charge, to calculate the formal charge for each atom, you start by determining the number of valence electrons that the atom in question brought to the molecule. So that's the same thing that we got from the periodic table. From that, we subtract the number of unshared or lone pair electrons on the atom, and then we subtract the number of bonds. Okay? So let's take a look at this for methane and for ammonia. So for carbon, the formal charge is equal to the number of valence electrons, which is 4, minus the number of unshared electrons, which is 0, minus the number of bonds. So that equals 0. In ammonia, looking at it for nitrogen, we have 5 valence electrons from the nitrogen minus 2 electrons in lone pairs minus 3 bonds, and that again equals 5. So there are some other ways to do this calculation that are all equivalent. Whatever works best for you is what you should go with. Okay, so now as we were talking about on the last slide, we said that with the exception of hydrogen, which only has room for 2 electrons, almost all atoms and elements that we draw in Lewis dot structures are going to have 8 electrons, which is to say they follow the octet rule. But there are a couple of exceptions of this. The first has to do mostly with elements that are in the 3rd row, and we'll see this most in organic chemistry with boron and aluminum. They tend to only form 3 bonds, at least when they have 0 formal charge. So some examples like that would be BH3, this hydroborane. So in this case, since the boron only has 3 valence electrons, and the hydrogens are another 3 valence electrons, we only have 6 total electrons to work with, so there's no way the boron could get 8 electrons. So it's going to be satisfied to only have 6. This will give us some predictions about the reactivity of hydroborane, but we'll talk about that a little bit later. For a molecule like the trifluoroaluminum here, in this case, the fluorine has a lot of lone pairs of electrons, so we could conceivably draw double bonds here to give the aluminum 8. But that would end up putting a positive charge, formal charge in the fluorine, and that's a very electronegative atom, so that's just not a very likely structure. And we'll talk about things like that a little bit more. So basically what you can remember is that boron and aluminum often will only have 3 bonds or 6 valence electrons. What you really want to be careful about in almost all situations, though, is putting more than 8 electrons on any atom. If you do that, you've usually made some sort of mistake, with one exception. And that exception has to do with elements in the third row of the periodic table or below. With regard to organic chemistry, we're mostly just going to see that for sulfur and phosphorus. There are some other possibilities, but those will be the main ones. Now, if you remember the orbitals that are available for bonding, once we get to the third row of the periodic table, in addition to the s orbitals and the p orbitals, we also have d orbitals. Okay, so there's essentially room for more electrons to fit in. So in that case, we'll sometimes get better Lewis dot structures with fewer formal charges if we end up putting 5 or 6 bonds on a sulfur or a phosphorus. So one example that we're going to see all the time is sulfuric acid, or H2SO4. This is a very common reagent in organic chemistry, so we'll see this a lot. And the best Lewis dot structure that can be drawn for this ends up having 1, 2, 3, 4, 5, 6 bonds, or 12 electrons on the central sulfur atom. All of the oxygen atoms follow the octet rule, and the 2 hydrogens have 2 electrons. Similarly, with a lot of molecules that contain phosphorus, it's possible for the phosphorus to have more than 8 electrons as well. So in this molecule, this trimethylphosphine oxide, we have 5 bonds on the phosphorus for a total of 10 electrons. Okay, we will never see more than 8 electrons, though, on second row elements, carbon, hydrogen, nitrogen, oxygen, and fluorine, and it's pretty uncommon on chlorine and bromine as well. All right, so that was kind of just a brief review of some of the factors in dry and Lewis dot structures. If you want to be able to do this quickly, though, you really just need to learn the information that is in this table, because this is presenting the sorts of bonding patterns that are most common in organic chemistry. Okay, so for the 3 most common atoms that we see in organic chemistry other than hydrogen, let's take a look at their common bonding patterns. So the most common, of course, is carbon, which has 4 valence electrons. And in a molecule, we'll tend to see carbon bonding in one of 3 ways. The most common is that it has 4 bonds, so that's in the middle here. And with 4 bonds, it's going to have 0 formal charge. Okay, now those might be 4 single bonds, or 2 single and a double, and 1 single and a triple. That doesn't really matter at this point, it's just that there's 4 bonds. We can also have a carbon where we have 3 bonds and no lone pairs, okay, and that would be the situation on the left here. Let's see how am I make that work. Okay, that's the situation on the left here. And in that situation, we have 1, 2, 3 bonds and no lone pairs. So if you remember the formula for formal charge, in that situation, the formal charge is going to be equal to 4 valence electrons minus 0 lone pairs electrons minus 3 bonds. That's going to equal 1. And when we see that an atom in a molecule has a charge of 1, typically we will just show that by putting a positive charge there. And now when I draw positive charges on structures, I often like to put a little circle around the positive charge or the negative charge, just so it's a little bit easier to identify. Okay? Similarly, if we have a carbon that has 3 bonds and a lone pair, that is going to have a formal charge of -1, and we'll mark that with a negative charge. Okay? So we can go ahead and do the same thing with nitrogen and oxygen. Nitrogen is neutral, or has 0 formal charge, when it has 3 bonds and 1 lone pair. It's positive when it has 4 bonds and no lone pairs, and negative when it has 2 bonds and 2 lone pairs. And you can go on and work that out for yourself with oxygen, okay? Most of the time in most molecules, especially if the molecule overall doesn't have a charge, all of the atoms are going to have 0 formal charge. So the most common bonding structures we see is a carbon with 4 bonds, a nitrogen with 3 bonds and a lone pair, in an oxygen with 2 bonds and 2 lone pairs. There are some exceptions to that. There's some molecules that will always have formal charges, but that's really the most common. So if you can remember the information in this chart, drawing Lewis dot structures of organic compounds is going to be really pretty quick and easy. No, not too far. Okay, so now that we've just done a quick review of drawing Lewis dot structures without saying very much about what they mean, let's get a little deeper now into the physics of this, okay? So how organic chemists think about bonding, of course, is that an electron from each of the atoms is involved in making a bond, okay? But now when we think about electrons, when we talk about them in atoms, we don't just have them, randomly circling the nucleus. Instead, they reside in orbitals. So let's just do a little review of orbitals, okay? So orbitals are the potential spaces that electrons can reside in, and their shape is derived from complicated mathematical formulas that we organic chemists don't really like to worry about. So instead, we sort of think about their shapes. The simplest orbitals are the s orbitals, which have a spherical shape. And next are the p orbitals. And these are often referred to as being dumbbell shaped, which I don't really understand why that terminology came from. They tend to look more like figure eights, okay? So they have 2 what are called lobes, and the electron density is distributed between those 2 lobes, and there's none of it in the middle here. Now, at a given energy level, there are going to be 3 p orbitals, and we say that they are aligned either along the x-axis, the y-axis, or the z-axis. So we refer to those as the px, the pz, and the py orbital. Okay? As you go to higher energy levels, you can see there are more complicated orbitals. So for instance, once you get to the 3rd energy level, then you have the possibility for d orbitals, and there are 5 of those, and it goes on to f and g and h. In organic chemistry, we really just worry about the s and the p and the z. Sorry, the s and the p. We don't really worry about the d or anything higher. Okay? Now, when we talk about a carbon atom, because that's what we're really going to be mentioning here, okay, so remember, a carbon atom has 6 electrons, okay? And when we talk about where the electrons reside in a molecule, they tend to want to be in the lowest energy orbital that is possible. So these different orbitals have slightly different energies. And we can see that on this energy diagram over here, okay? So you probably drew this sort of diagram in general chemistry, where we use arrows to show the location of the electrons, and we build them up from the lowest energy to the highest energy. So carbon, which has 6 electrons, 2 of them are in the lowest energy 1s orbital. The next 2 are in the 2s orbital. So that's 1, 2, 3, 4, and we have 2 left. So there's 1 in 2 of the 3 p orbitals, okay? And now I drew those as sort of single hooked arrows with pointing up or down. That isn't really that important for organic chemistry, but we just want to think that we have what we want to remember is that we have these electrons that reside in orbitals of different energies, okay? Now, when we're talking about these, the electrons in this 1s orbital, we refer to these as core electrons, and they are not going to be involved in bonding because that energy level is full, okay? The ones in the second energy level, in the 2s and the 2p, these are the ones that we call the valence electrons. Okay, so overall that second energy level isn't full, even though that individual 2s orbital is. So these electrons are going to be available for bonding. Okay? Now, to make things a little more complicated, though, the bonding occurs when orbitals from two different atoms overlap and those atomic orbitals combine to form something known as a molecular orbital. So a bond can be considered to be a molecular orbital that contains two electrons. But if you look at the geometry of the orbitals that we have available in carbon, the S, and the P, remember what their geometry looks like is the S orbital, is a sphere in the middle, and we have the three p orbitals that are all mutually orthogonal or 90 degrees apart from one another, okay? And that does not correspond very well with the bond geometries that we see in carbon. So if you remember talking about VSEPR theory, we'll talk about that a little bit later, carbon tends to have what's called a tetrahedral geometry with about 109.5 degree orbitals, okay? So the way that we explain this is that before the atomic orbitals from different atoms combine to form a bonding molecular orbital, they first kind of shuffle with themselves or mix in a process known as hybridization. Okay? So hybridization is a mixing of atomic orbitals that allows for bonding. Okay? And in organic chemistry, we're going to predominantly talk about mixing or hybridization of s orbitals with p orbitals. Okay? And kind of the way that I like to think about this is that you imagine that we are throwing our orbitals separately into a blender, mixing them all out, and then pouring them out again. Okay? So if you put 1 cup of orange juice and 3 cups of pineapple juice into a blender, mix it all up, you're going to end up with 4 cups of something that is a mix of orange and pineapple juice. Okay? Kind of the same thing happens with the orbitals. Okay? So one of the most common hybridizations that we're going to see in carbon occurs when we mix the 2s orbital, of which there is one, with all 3 of the p orbitals, okay? So we are mixing 4 orbitals to start with, and that is going to give us 4 new hybridized orbitals, okay? And these hybridized orbitals, because they are made up from a mixture of an s orbital and 3 p orbitals, have the name sp3. So we call these sp3 hybridized orbitals, okay? And that's going to be the hybridization that carbon atoms have whenever the carbon has 4 single bonds, okay? So the way that bonding occurs in a molecule such as this is ethane, C2H6, or ethane, okay? And let me just draw the Lewis structure for this quick. We have our 2 carbons attached to one another, and each of the carbons is then bonded to 3 hydrogens, okay? So the orbital bonding configuration of this is that each of these carbon atoms is sp3 hybridized. So it has 4 sp3 orbitals that are available for bonding, and that's how it's going to get to 1, 2, 3, 4 single bonds, okay? In all of the bonds that are happening here are going to be caused by the direct overlap of atomic orbitals from 2 different atoms. So the central bond between the 2 carbons is an overlap between an sp3 from one of them and an sp3 from the other. And whenever we have a bond that occurs from the direct overlap of atomic orbitals, that is referred to as a sigma bond. Okay? Now, we have 2 different types of sigma bonds in this molecule. our carbon-carbon sigma bond is an sp3-sp3 sigma bond. Our carbon-hydrogen sigma bonds, on the other hand, are caused by the overlap between the sp3 hybridized orbital of the carbon and the non-hybridized s orbital of the hydrogen. Okay, so hydrogen only has one type of orbital, so it can't undergo hybridization. Okay, so this is still a sigma bond, but we would call this a sigma carbon sp3 to hydrogen s. Okay, and the center one, we call that would be a sigma bond that is a carbon sp3 to carbon sp3. Okay? When an atom is sp3 hybridized like this carbon, its geometry is said to be tetrahedral. Okay, so that means, so a tetrahedron is just a fancy way of saying a pyramid, that is three-sided. So it's a shape that has four sides that are all triangles. We have our carbon in the center, and if we draw lines going out to the four vertices, that looks a lot like the geometry of carbon in most molecules. So we call that a tetrahedral geometry, and the bond angles are about 109.5 degrees. Okay, so that's the first hybridization that we're going to see. The second type of hybridization that we're going to see occurs most likely when we have carbon-carbon double bonds, and these are going to tend to have what is called sp2 hybridization. Okay, so if we have sp2 hybridization, by the same logic that we used for sp3, what that is going to mean is that instead of mixing the s orbital with 3 p orbitals, we're only going to mix the s orbital with 2 of the p orbitals. Okay? So that is going to leave us 1 of the p orbitals remaining. So now the valence orbitals that are available for bonding are going to be 1, 2, 3 sp2 orbitals and a single remaining p orbital. Okay, so this p orbital is not hybridized. And these sp2 are, okay? And in general, hybridized orbitals are used to make sigma bonds. Okay, so if we look at the Lewis dot structure here of this molecule ethene, we have a carbon-carbon double bond, and each of the carbons has 2 single bonds to hydrogen. Okay, the orbital picture of this is that we can see up here is that each of our carbons has 3 sp2 orbitals, one that points straight towards the other carbon atom, and the other 2 that are pointing away. Okay, and all 3 of these orbitals are in one plane. So let's call that the xy plane. Okay, so this bond in the middle is a sigma bond from the overlap of sp2 orbitals from the 2 carbons. Okay, so that describes the sigma bonding framework similar to what we've seen before. But when we have sp2 hybridized orbitals, we have another type of bond, and that is known as a pi bond. And a pi bond arises when we have the side-on overlap of p orbitals. And for that to be really effective, the p orbitals have to be parallel to one another. Okay? So in the geometry of the molecule here, they are both going straight up and down. Okay, so since when they are aligned, they can kind of merge together to form what is known as a p as a pi orbital or a pi bond. Now, because those bonds do not have the direct overlap of the orbitals, they tend to be a little bit weaker, and that's going to be kind of a useful thing for predicting reactivity. Okay, so what's important to note is that hybridized orbitals form sigma bonds and p orbitals form pi bonds. All right, now there's just one last type of hybridization that's pretty common, and that's going to be the sp orbital. And that's most commonly seen in molecules that have a carbon-carbon triple bond. So that will have sp hybridization. Okay? So to get sp hybridization, as you might imagine, that's going to occur when we mix the s orbital with only one of the p orbitals. So that is going to give us two sp orbitals, and they're going to be oriented 180 degrees apart from each other, and the remaining two p orbitals are going to be orthogonal to that. So in this case, if we have the blue orbitals going from left to right, those are sp orbitals. The orange p orbital is going to be up and down, and the purple one is going into the plane and out of the plane. So they're all 90 degrees apart from each other. So this is the common hybridization when we have triple bonds in a molecule like this one known as ethine or acetylene. And in this case, we have a carbon-carbon triple bond. One of those bonds is the sigma bond between the two sp orbitals. The other two bonds are pi bonds, one from the orange non-hybridized p orbitals, which are parallel, and the second from the purple. Okay, so this molecule has sp hybridization. We say that it has a linear geometry, and the bond angles are 180 degrees. Okay, and we'll take a look at some practice problems to look at that. Now, the last thing that I want to talk about today is just a little bit of shorthand that organic chemists use in writing molecules that makes it a lot easier to draw structures clearly and quickly. And that is something that is known as the bond line structure, or sometimes this is called the skeletal structure. Okay, so there are kind of three main ways that organic chemists can use to draw structures. The one that has the most information are the Lewis structures, as shown here. Okay, now in this one, we've kind of shown the carbon-carbon bonds as being in a zigzag. Really, the geometry in a Lewis structure doesn't matter because we're just showing the connectivity. Okay. One other way of drawing structures that we won't be using very much in this class, but is useful to be able to identify, is something called the condensed structure. And the condensed structure, you list all of the atoms of the main chain, in this case the 4 carbons, with their substituent atoms after them with subscripts to show how many there are. Okay? And this is really most useful if you're imagining trying to describe a molecular structure using a typewriter or a word processor or something. So you might see this a lot in catalogs or in text. When you're drawing freehand or using drawing software, you don't bother with those very much, okay? So we're going to mostly use our bond line structures, okay? So what are the rules or the conventions for drawing bond line structures? Well, essentially what's going on in a bond line structure is that this is very much like a Lewis structure, where we don't draw the letter C for carbon atoms, and we don't draw the letter H for the hydrogen atoms, okay? So if you imagine this Lewis structure, but we just erased the carbon-hydrogen bonds, and we erased all the letter H's, that would give us this bond line structure, okay? So if we have a structure like this, we have that means that we have a carbon atom at any intersections, sort of any V's, or the end of any lines. And also, anytime we transition from one bond type to another, like say from a single bond to a double bond or a single bond to a triple bond, there has to be a carbon in between those, okay? Because remember, bonds are the connection between atoms. What greatly simplifies these bond line structures is that we don't have to explicitly draw the hydrogen atoms, okay? We just know how many there are based off of those bonding rules that we saw earlier. And pretty much the rule for this is that to figure out how many hydrogens there are in any carbon atom, we just subtract the number of bonds to the carbon atom from 4, okay? Because carbon wants to have 4 bonds in a molecule. Now, if we have formal charges, that gets a little more complicated, but we'll see a little bit more of that. Any other atoms in the molecule are shown, and hydrogens that are bound to other atoms, like oxygen or nitrogen, are shown. And in general, lone pairs of electrons are optional. Because they are, it's useful to see where they are, it's good to be able to draw them, but you don't necessarily have to, okay? So let's take a look at the following two bond line structures and see if we can determine how many carbon atoms there are, and for each of those carbon atoms, how many hydrogens are attached to it. Okay? So this molecule on the left, this is a molecule that has 3 single bonds and 1 triple bond. And remember, when we go from a single bond to a triple bond, there has to be a carbon atom there. So this molecule has 1, 2, 3, 4, 5 carbons. Okay, and now for each of those carbons, let's count how many hydrogens there are. Remember, that's going to be 4 minus the number of bonds to that carbon atom, or number of bonds that are drawn explicitly. So for this first carbon atom, there's 1 bond drawn, so that means there are 3 hydrogens. For the second one, there's 1 bond from the single bond and 3 bonds from the triple bond, so no hydrogens. Again, 3 bonds to the triple bond and 1 to the single bond, so no hydrogens. The next carbon down the chain has 2 bonds drawn explicitly, 1, 2, so that means it is going to have 2 hydrogens. And the one on the end has only 1 bond, so it's going to have 3 hydrogens. Okay, so if we count that all up, that's 1, 2, 3, 4, 5, 6, 7, 8. The molecular formula of this molecule would be C5H8. Okay? Now we can do the same thing for the nitrogen-containing molecule on the right. I'll put a dot for each of the carbons. There's 1, 2, 3, 4, 5 again. And we can quickly determine how many hydrogens are on each. Okay, we have 3 on each of those 3 carbons. The one that's in the middle here has 4 bonds, so it doesn't have room for any hydrogens. The next carbon down the chain has 2 bonds and therefore 2 hydrogens. Okay? So now something that's a very useful skill is to be able to convert relatively easily between full Lewis structures and bond line structures. Okay? So what is shown in the molecule at the bottom here is the Lewis dot structure of glucose, blood sugar, or really one of the main carbohydrate involved in metabolism. So let's see if we can draw this as a proper bond line structure. Okay, so you can see that kind of the central structural feature of this is this 6-membered ring that has 5 carbon atoms and an oxygen. So when we're drawing that, we can draw that as a hexagon, but we need to have the oxygen shown explicitly, and then we can draw just lines or bonds to show all the carbons. 1, 2, 3, 4, 5, and then a bond going to the oxygen. Okay? We don't have to show any of the hydrogens attached to the carbon, but we do have to show any hydrogens attached to the oxygens. Okay? So we can go through for each of the carbons in the ring, and we can see that they are attached to an oxygen with a hydrogen. Okay, and so that gives us our Lewis dot structure. Now, if we wanted to be really thorough, we could go through and put in the lone pairs of electrons as well. I'll do those. Oh, that didn't work. Oh, I erased instead of drawing. This is my first time with the software. I'm sorry. Okay. So we're going to have 2 lone pairs on each of those oxygens. Okay. And now something I just want to point out, a couple of things. The first is that when I showed, and we did it on both sides here, this OH group, I didn't show the bond between the oxygen and the hydrogen. This is exactly the same, though, as drawing that oxygen-hydrogen bond explicitly, okay? So it's up to you in a given situation when you have a hydrogen attached to an oxygen or a nitrogen, say, whether you just want to draw them together as an OH or whether you want to show the bond. And depending on what you're trying to convey, either of those is fine, okay? You'll also see over here that sometimes I wrote OH and sometimes I wrote HO. Typically, I don't want to put the hydrogen in between the oxygen and the other atom that it's attached to. Okay, it just looks better to me that way. Okay, so these are just some subtleties that you'll pick up by doing this with practice. Okay, and that appears to be the end. I thought I had one more slide, but I don't. Thank you very much.